I'm Charlie Bryant, and this is Lab 2. In it, we will be tracking the motion of a falling object. First, we'll observe an object's motion using Tracker, and then we'll make a couple computational models comparing the motion of if the net force is only due to gravity, and then we'll see what happens when we add in some drag force. These are the key principles working in the lab. First, we have Newton's second law, which tells us that the final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. Since in this lab the net force will not be zero, our final velocity or initial velocity will not be the same. Now look at the free body diagram to the right. These are the two forces acting on the object to make the net force. The drag force is calculated by the drag force coefficient, which is specific to the object in motion, we'll talk about it later, times the magnitude of the velocity squared. And then the weight is just equal to the object's mass times the force of gravity. We put a negative sign there because it's always in the downward direction. Here's our setup. The hat is the system, and everything else is the surroundings. Notice that I represented the drag force with a smaller error than the weight. Those aren't to scale, but we know that the net force is down since the object falls in that direction. Using Tracker, I tracked the object's center of mass through frames of about 1/30th of a second long. Note how the intervals between the points increase as the object accelerates due to gravity. Here's a simple position versus time graph for the data from Tracker. I included a line of best fit to account for the human error when plotting the positions. Now we're going to get to a computational model using VPython. Remember that the net force is only due to gravity in this model. Here's the code in VPython. First we need to input the object's mass, starting positions, and time interval, which I set to be the reciprocal of the frame speed of the camera. The drag coefficient is also set here, and we'll get to that later. This while loop uses Newton's second law with the net force equal to the gravitational force of the object, and outputs that data that we can observe in a graph. As you can see, the gravitational model predicted the object falling much further than it actually did. That's because we didn't account for the drag force at all, which would have diminished the magnitude of the net force since it is in the opposite direction of the gravitational force. Now we're going to make another computational model using VPython. This time, it's going to be gravity plus the drag force. Remember the equation from the first slide. Our net force is equal to the force of air plus the weight. Everything else in the code is the same, except I added an equation for the drag force and included that in the calculation of the net force. The drag coefficient, shown here as b, was deduced on a trial and error process. We knew from the experimental data where the object's final position should be, so I tried different b values until the computational final position was equal to that of the experiment, to 3 decimal places. This gives us a realistic approximation for the drag force in our model. The drag force model in purple is a much closer match to our actual data, since the net force is a much better approximation of what it was in the experiment. So what does this mean? Can we predict terminal velocity? The answer is yes, we can, provided, of course, that we're able to accurately calculate the net force. I found the actual terminal velocity by using my last data points in my experimental I found the actual terminal velocity by using the last 2 data points from my experimental data. This turned out to be negative 0.34 meters per second. Notice that this is much closer to our predicted terminal velocity from our drag force model, where it predicted that the terminal velocity would be 0.29 meters per second, much closer than the negative 0.71 predicted by our gravitational model. So what if the object doesn't start from rest? That's a good question. Let's use VPython to compare the terminal velocities. So everything else in the code was exactly the same as the last time I ran the drag force model, with one key difference. The ball's velocity started off with negative 1 meters per second in the y direction. Using the same method as before, I found the terminal velocity when the initial velocity started at negative 1 meters per second. The rise over run in this case happened to finish at negative 1.29 meters per second. So the increase actually happened to be the same in both cases. That's interesting. And now some thoughts as we part ways. Real-world falling objects will never outstrip their computational models unless they're in a vacuum, in which case they'll only be equal. We can predict the terminal velocity of objects as long as we can accurately calculate the net force. Having an initial velocity does affect the final velocity. I mean, after all, it's right smack dab in the middle of Newton's formula. Okay guys, thanks for listening.